So these are the rules for balancing redox reactions. It's a seven-step process. It's a little more complicated than balancing regular reactions because what you have to make sure you do is balance all of the charges. We have to not only concern ourselves now with how many and which type of atoms are each side, but we have to have the right number of electrons on each side. And quite frequently, water will be involved, either donating or accepting electrons. If it's in an acid environment, hydrogen ions might be moving around or adding or accepting electrons. If it's in a base environment, hydroxide will be involved with all of this. So what we're going to use is what's called the half reaction method. We're going to balance each half reaction, the oxidation half and the reduction half. We're going to balance each of those, get all the electrons right, make sure we have the same number of electrons on each side, and then put them back together. So here's the 7 steps, and keep this in front of you as we do our sample so we can go back and double check to make sure we're doing it right. Alright, so here's our sample problem that we want to try to balance. It's redox. We have things shifting around. The first step is to put in all the oxidation numbers. So let's start taking a look at these. I'll start with the ones that are definitely following the rules. Oxygen is going to be a -2 when it's combined in every case. So we can fill those in. Manganese 2, it's an ion by itself, so it's going to be +2. Now we can start filling in the other things. If we have 2 -2s for the oxygen, carbon is going to have to be a +4 to cancel that out. Here we have 4 -2s, that's -8. We have 2 carbons, but we need to add up to -2. So the 2 carbons together are going to have to be +6. So each carbon will be +3. +6 and -8 gives us -2. And for the permanganate ion, I have 4 -2s, that's -8, but I want it to add up to -1. So manganese will have to be +7. So let's take a look at which is being oxidized and which is being reduced. Manganese is going from +7 to +2. The number goes down, that's being reduced. So we can write our reduction half reaction as the permanganate ion yields the manganese 2+ ion. For oxidation, the oxygen's not changing, but the carbon is going from +3 to +4. So I can write the oxalate ion is going to make carbon dioxide. Now if we take a look at the next step is to start adding things and balancing things out. Our next step then is to balance all the elements that aren't hydrogen or oxygen. And so if I look at the oxidation, I've got 2 carbons on the left, I need 2 carbons on the right, so let's put a 2 there. Here I've got manganese 1 on each side, so I'm all set with that. Now we balance oxygens by adding water. So here I've got 4 oxygens on the left, I'll need 4 oxygens on the right. Each water gives me 1 oxygen, so I'll need 4 waters on the right. Here I've got 4 oxygens, here I've got 2 times 2 is 4 oxygens, so that one's all set. The next step, which is step 4C, is adding hydrogens by adding H pluses. Well, in oxidation, I don't need any hydrogens, so we didn't add any waters. For the reduction, I have 8 hydrogens on the right, so I need to add 8 hydrogens on the left. Now 8 hydrogens, 4 oxygens, 1 manganese, 1 manganese. For oxidation, 2 carbons, 4 oxygens, 2 times 2 is 4 oxygens. Now I have to look at the overall charge and balance that by adding just electrons. So in the oxidation, on the left it's -2, so I need to add 2 electrons on the right to balance that out. We only add electrons now. Here, on the reduction, I have 8 pluses and a minus. So overall, this whole side is +7. This side is +2. Now I need to add electrons, which is adding negatives. So I'll add it to the side that's the more positive. So I'll add, see, I need 5 electrons to the left. Now I have to figure out how to get these all the same number of electrons. So what do I multiply each side by to get the same number of electrons? Well, lowest common multiple. Between 2 and 5, the lowest common multiple is 10. So I'll multiply everything on this side by 5. So 5 oxalates makes 5 times 2 is 10 CO2s and 10 electrons. This side, everything is multiplied by 2. So 16 hydrogens plus 10 electrons plus 2 permanganates will make, and again we're multiplying by 2 manganese 2s, and 4 times 2 is 8 waters. Now all I have to do is combine everything into one reaction again, and then make sure I eliminate anything that's the same on both sides, and that'll be the electrons, and sometimes waters. So I'll just start over here. 5 oxalates plus, now over to the reduction side, 16 hydrogens plus 10 electrons plus 2 permanganates yields, now on the right, 10 carbon dioxides, 10 electrons, 2 manganese 2 ions, and 8 waters. Eliminating what's the same on both sides, I get rid of the 10 electrons on both sides. Everything else is exactly as it should be. 5 oxalate ions plus 16 hydrogen ions plus 2 permanganate ions will make 10 CO2s plus 2 manganese 2s plus 8 waters. And we can double check to make sure this works. 5 times 2 is 10 Cs, 10 Cs. For oxygens, I have 5 times 4, that's 20, plus another 8, it's 28. Here I've got 10 times 2 is 20, 8 times 1 is 8, 28. 16 hydrogens, 8 times 2 is 16 hydrogens, 2 manganese, 2 manganese. And if we check the charge, 5 negative 2s, that's negative 10. Here we've got plus 16. Here we've got negative 2. That's neutral. Here I have 2 plus 2s. That's plus 4. Negative 10 plus 16 is positive 6. Minus 2 is positive 4. Positive 4 on the other side. Everything balances, including the charges. We've now done this right. Okay, I just noticed that in the previous video you couldn't see the whole final reaction. So I've backed the camera up a little bit. You can see the entire final reaction, all the way from the oxalates across to the 8 waters at the end. These are some very common redox reactions that you might see in a lab or on a test. If you have any metal oxide in water, you're going to end up making the metal hydroxide. And we did this in the big long lab with 20 reactions. We used calcium oxide, but same thing with barium oxide. If you have barium oxide, you add it to water. It's a fairly exothermic, fairly vigorous reaction to make barium hydroxide or calcium hydroxide. We tested for the presence of the hydroxide ion by using the litmus paper, and you should have had it turn blue when you tested the solution of calcium oxide in water. If you have a non-metal oxide in water, it ends up making an oxyacid. So, for example, nitrogen oxide in water will make, in this case, nitrous acid. It could make nitric acid. If you have a sulfur oxide in water, it will make sulfuric acid. If you have a chlorine oxide in water, it will make a perchloric acid or a chloric acid. If you have a phosphorus oxide, it will make phosphoric acid. Now, it's not quite so obvious which one it will make. Will it make nitrous or nitric acid? That you don't have enough information to know right now. If you just go with the nitric acid or the sulfuric or the phosphoric, the ic acid, you'll be fine. You'll get the points for that, because absent of any other information, you're not going to be able to predict which it's going to make.